right, moving into chapter 9 here. Chapter 9 is going to be kind of weird for us because we're getting away from the main focus of calculus, and we're moving into differential equations. This is just supposed to be kind of an introduction to differential equations, and hopefully you saw a little bit even in Calc 1, and we'll kind of review that some as well once we get into section 2 of chapter 9 for us. But this is also kind of a prequel for those of you that are moving on to the differential equations class that we have here at Craven. Yeah, so let's just kind of jump right into it. So this is mostly an intro, mostly a review, so it's going to be kind of bouncing around quite a bit. First thing we want to talk about is this definition here for first order differential equations. So a differential equation is any equation that you write down that has a derivative in it anywhere. A first order differential equation is any differential equation that can be written in this form where you have the derivative is equal to some function of x and y. In other words, you can solve for the derivative. Okay, we have to be a little bit more careful about it. So that function f of x, y on the other side is a function in two variables defined on the xy plane. Okay, it is called first order since it deals with the first derivative. There are equations out there that have the second derivative, third derivative, fourth derivative in it. Anytime you have a differential equation that only has the single derivative in it, it's called a first order differential equation. There's a couple different ways that we can notate this as well. So of course we could write the derivative as y prime like that and set it equal. Or another way that some people write it out is just to have the derivative notation out in front of the function like that, f of x, y. So if you see it written any kind of way like this, just know it's talking about the same thing. Okay, moving on from that. A solution to this differential equation is a differentiable function, y equals f of x, defined on some interval I. So a lot of times with differential equations, it's not a solution that is true everywhere. It's only true on a small interval. We're not really going to be playing around with this too much. That's something that if you do move into the differential equations class, that's something they focus on a little bit more. So there's two different types of solutions to these differential equations. There's what's called the general solution. The general solution to a first order differential equation is a solution that contains all possible solutions. Okay, so a lot of times with differential equations, if you're just given the differential equation, it's actually going to have a family of solutions to it. It's only when you're given a set of initial conditions is it going to then have just one possible solution. And that one possible solution we'll define here in a minute. Before we get to that, let's look at a quick example. So I think you'll have something like this on the homework. These are pretty easy. So show that y equals c over x plus 2 is a solution of the first order differential equation. Dy dx is 1 over x times 2 minus y on the interval 0 to infinity. How do I put infinity in here? Okay. Where c is any constant. Okay, so before we like jump into solving this one, although it's easy, you just plug it in. This is what we're going to call a general solution. A general solution is any solution that has this unknown constant in it, and it doesn't matter what that constant is. It could be any number. It still solves the differential equation. So this is what we would call the family of solutions. Finding that particular c would then be finding the particular solution. Okay, so to solve this one, all we do is we just plug it in to the differential equation. So we'll plug it into both sides separately. Let's first plug it into the left-hand side. Plugging it into the left-hand side of the differential equation just says to find the derivative here. So the derivative of c over x plus 2 would be negative c over x squared. The 2 would just go to 0. Okay, let's look at the right-hand side. So the right-hand side of the differential equation is 1 over x times 2 minus y. So that 1 over x stays, but it's going to be 2 minus y, which is c over x plus 2 from up here. So just substituting in c over x plus 2 for the y on the right-hand side of the differential equation. Then if we simplify this down a little bit, we have 2 minus 2, that's going to cancel out to be 0. And then we have 1 over x, and then negative c over x, which multiplies together to be negative c over x squared. So we're done, right? So since the equation is the same on both sides, then that y equals c over x plus 2 is a solution. And not just a solution, but the general solution. Or it's, anyway, doesn't matter. Let's move on. So sometimes, like I was saying, they're not just going to ask you to solve for the general solution, they're going to ask you to solve for a particular solution, and that's when they give you these initial conditions. So in most cases, we need a particular solution found using an initial condition. So that initial condition, we usually label it x naught, y naught. So if I plug x naught into y, it'll spit out y naught. You can think of it like the ordered pair, x naught, y naught. When we do find this particular solution, we don't call it a differential equation anymore. We call it a first order initial value problem. So if initial conditions are given, we call it an initial value problem. So just a real quick example, kind of like the one we did before. Show that the solution y equals x plus 1 minus 1/3 e to the x is a solution to the the initial value problem. Dy dx is y minus x, given the initial condition y of 0 is 2/3. Okay, same thing. So to solve this, we're just going to plug it in. Again, we'll plug it into the right-hand side and the left-hand side. So first things first, the left-hand side just says to take the derivative of my potential solution. The derivative with respect to x, that x is going to go to 1. This 1 goes to 0, and then negative 1/3 e to the x goes to negative 1/3 e to the x. Okay. The right-hand side of the equation is the x plus 1 minus 1/3 e to the x. Plugging y into this isn't going to change anything. We're still going to have the same thing. Oh, geez, I'm messing this all up. I don't know what I'm thinking. I was looking at the right-hand side here. I thought that looked weird. I'm supposed to be looking at the right-hand side of the differential equation. We're plugging it into y minus x. So, substituting in y, that's this x plus 1 minus 1/3 e to the x. And that's going to be minus the x. So what's going to happen is that my x is going to cancel out on both sides, and we end up with the 1 minus 1/3 e to the x. So yes, that is true. Now that's still not quite enough, because we also have to see if it solves my initial conditions. To do that, we're just plugging 0 in for the x and 2/3 into the y of the solution over here. So I'm going to get 2/3 on the left-hand side is equal to 0 plus 1 minus 1/3 e to the 0, and that comes out to be 2/3, right? You just get 1 minus 1/3. Okay, so not only does it solve the differential equation, but it also solves the initial conditions. So this really is a solution to our initial value problem. All right, moving on. So I know we haven't talked about any techniques yet for actually solving these differential equations, so we're going to get into that now. But we're not going to be talking about normal techniques for actually finding actual solutions. We're going to be looking at techniques that are more often used in the field, because a lot of the times we don't actually care what the equation of the solution is. We just need to know either the pattern or we need to know the numerical answer. So there's two different ways that we can do that. One way is something called a slope field. So let's just define this first. Solutions are in this form, right? Y equals y of x. That's the same format that the solutions to the differential equation are. So they can be graphed. And they can be graphed in such a way that the derivative is that differential equation, the y prime is equal to f of x, y. So that's usually what we're given. And remember, the derivative is just the slope. Okay. So this sentence is kind of awful, sorry about that, but you're given this, right? You're given the differential equation. The solutions to this differential equation are functions y of x. Because we are given the differential equation usually where it's solved for the derivative, that means that I can find the slope by just plugging xy into the differential equation to get the slope. Then graphing small segments of the slope on the coordinate plane creates what we're going to call the slope field. Okay, one more thing to write down here, solution curves are going to follow the fields. I'm going to jump over to the book now because it's too hard for me to graph on my own. If I had MATLAB ready to go at the moment, I would be graphing this stuff in MATLAB. So I might come back to this a little bit once we get MATLAB all set up, and that'll be something that I'll have you guys do. But let me just pull up the book here. Okay, so let's look at this example first, and we'll look at these other ones down here on the right. So this example is the slope field for y prime equals 2y minus x. So that's my differential equation here. To find the slope field, we just look at the different ordered pairs. So let's say we're at the point 1, 1. So my x is 1 and my y is 1. We're looking at this. The way that they got this small little line segment here is by plugging the ordered pair 1, 1 into the right-hand side of the differential equation. So it's going to be 2 times my y value, 1, which is 2, minus my x value, which is 1. 2 minus 1 is 1. So when I plug this ordered pair into the differential equation, I get 1. And this is a positive slope of 1. If I plug the next point here, 2, 1, into the differential equation, I would get 0, which is why I have a flat slope. Every single one of the ordered pairs in your plane is plugged into the differential equation to get the slope at that particular coordinate. Okay, let's look at these other examples here. So, here we have 3 more examples with 3 differential equations. Let's just focus on this first one. So this is the slope field for the differential equations y prime equals y minus x squared. This is also called a direction field. Sometimes it's called a current field because you want to think of it like a river or the flow in like an ocean or something like that. So if you were to drop something into the ocean at different initial conditions, you can see the path that it would take. So these blue lines here are the solution curves to this differential equation. Same thing here for these next two. So I think they're pretty cool. I think slope fields are very interesting and they're very neat. Again, the whole point of them is that if you start at a particular ordered pair, if you just follow the curve, it'll kind of map out what the solution curve is going to look like. Okay, so that's slope fields. Let's look at, oops, sorry, wrong thing. The next thing that we're going to talk about. So the next big thing besides slope fields is something called Euler's method. Euler's method doesn't give us a graph of the solution, but it gives us numerical approximations of the solutions. So just some sentences here. Sometimes it is not possible to find an exact solution. Now this is true. 99% of differential equations are impossible to solve. There's only certain ones that the world knows how to solve right now. But Euler's method lets us at least get a numerical representation of the answer. Okay, instead, we can find a numerical solution. Okay, so Euler's method approximates a solution through linear approximations. Now there's a whole lot of math behind the scenes here of what's going on. And so I'm going to kind of gloss over that a little bit and just kind of get to the point. The point here is that if you're given a differential equation, so y prime is equal to f of xy. My finger stopped working there for a minute. You're also given the initial conditions here, so y at x naught is equal to y naught. We approximate using... so this should be something that's a little bit familiar to you guys back from Calc 1. You should have seen this. So this is what we call Newton's linear approximation. So L of x is going to be the y value. So you could write this as y naught, but we're just going to write this as y of x naught. That's going to be plus the derivative at x naught, y naught. Oh, sorry, this is just the derivative at x naught. I don't know why I put x naught, y naught. I was looking at the next line. Times x minus x naught. Okay, so this is the linear approximation for a function. Basically, if we have some kind of curve going through space, this is going to be the straight line that linearly approximates that curve just in a small little line segment. What we're going to do is we're going to substitute some of this stuff out for our differential equation. So this is how we are going to think about this. The linear approximation is that y value y naught plus the right-hand side of the differential equation, which is f of the previous point, x naught, y naught, times x minus x naught. All right, so really these two equations are exactly the same. It's just one of them is thinking about it like kind of a normal function. The bottom one there is thinking about it with our differential equation here. Okay, so what this thing that gives us, right, this L of x gives a good approximation over a short interval. So we will string a bunch of these LX's together. Okay, and then we get Euler's method. All right, so the way that we're going to write this out is that you're given that point x naught, y naught. If my fingers would work. There we go. So that's going to be like our initial point, right? We can find the next point, x1, y1. To find the next point, x1, y1, we're going to take the last point, x naught, and add to this value, h. H is going to be the step size. So to get to the next x value, we're just going to increase it by the step size h. And usually h is a pretty small number. To get the next y value, we're going to use that linear approximation. The next y value we get by taking the previous y value plus plugging the previous point into the differential equation times x minus x naught, but x minus x naught is just the step size h. Okay, then to get the next point, we would do the same thing. So x2 would just be the previous x value plus the step size. Y2 would be the previous y value plus plugging the previous point into the function times h. And you would just keep doing this and keep doing this forever and ever and ever. I have no idea how long this video has gotten. A little bit too long. What I'll do here is I'll stop this one and I'll make another video here just finishing up section 1.